Good morning, everyone. Once again, let me share my screen. And really, the topic of today's discussion will be dedicated to the main goal of your project, a modeling project while you are here. And we will try to teach you specifically how to fine-tune parameters within a given model. To do so, first let me start fresh copy of GX Simulator in the SSW ideal session. So it's loading. Now I'm going to import a model with which you already worked recently and during previous class is, I believe, this one. Now this model is being loaded, and this is one of the models with which you, at least two of you, will start working as soon as you are here at NJIT. This is a model which was used in a published paper. This is one of snapshots of this paper showing two time frames for which modeling have been produced, and this model relates to this particular time frame. And just scrolling up and down, this is paper, more or less recent paper, but not the most recent. And the data are from relatively old days, 2002, and this gives us some historical limitation for the modeling. You will be provided with the text of the paper for your studies, but here you can see time profile of hard X-ray, soft X-ray, and radio emission. Now, and this is how this model looks like in the perspective. This is a couple other views. So this is just useful entry information, and you will start from the model which fits this instance of time. Because of historical reasons, because in 2002 we did not have data to provide a really good magnetic data cubes, we used so-called linear force-free extrapolation, and this sort of models require top view consideration. So do not forget to check mark top view when you work with this model. Then we compute the rendering grid, zoom in. This is thermal plasma, which has no structure, and this is distribution of non-thermal electrons in this model. And now I will compute microwave emission, for which I upload GX Jersey synchrotron transfer routine. And final step, I have to import the reference spectrum, which is here. And with this reference spectrum, I have to move to the time frame for which this model has been created, and this is 17:45:09. 17:45:09. 4509. Yes. Let's double check. 09. Yeah. This correct time frame. So the idea is when I push the button compute emission, I hope the model spectrum will match the observed value. Here you see that we have a really good match of the spectrum. We just ignore this component that may be just irrelevant. We do not have sufficient information to work with it. We will concentrate on this main component for now. Okay, so what is your immediate assignment will be? You will move, one of you will move in the future, the other one into the past. So you will scroll down, change a little bit, and try to adjust parameters. In such a way that each time frame is more or less equally well fitted with the data. The time step here in this set of data is 4 seconds. So each click change time by 4 seconds. Now it's not. There is no much change right now, so I will keep moving to the right until I see a significant change of the spectrum. So spectrum somehow evolves, but it's not yet sufficient, I believe, to start adjusting parameters. Okay, so now something significant happened. So what we see here, we see that the optically thin high frequency part of the spectrum remains roughly the same, but the optically thick low frequency part of the spectrum moved down. I do not have time to make up for entire course of gyrosynchronization properties. Now, I will just give very fragmentary information of how parameters can affect the gyrosynchronous spectrum, but you will be given an assignment to make some homework, which will help you a lot further, during your summer. So the first question: what reasons can cause decrease of optically thick part of the spectrum? One possible reason is decrease of source area. Another possible reason is increase of the magnetic field at the source. Then if the source area goes down, but this segment remains roughly the same, this means that total number of emitting electrons remains roughly the same, which means that number density, number of particles per unit volume must go down because area and volume went down. The other possible reason, when magnetic field goes down, implies that for the same number of electrons, optically thin emission will go up. So if we try to match the spectrum with lower magnetic field, then having roughly the same high frequency part requires that the number of electrons went down. And to make tests, what may happen, I created a simple code. You will be provided with it, and you will be working with this simple code. I will show what it is doing. Play run, and here you see two spectra. The thin line is reference spectrum for, let's say, standard set of parameters. And thick one is the spectrum in which one of the parameters used for first one was somehow changed, adjusted. It's done here. In this case, I numbered the parameters. We have list of all available parameters here from 0 to 28. Some of the parameters are just technical, other parameters are physical. And here, when I change just one parameter, I remind that 0 means source area, 1 means source depth, 2 means plasma temperature, 6 means minimum, 7 means maximum, etc. So now what we are going to do now in this exercise, I will comment this one out, and I will play these parameters I just mentioned in the simulator to make an idea what to expect in our model. This simple program works with just simple single uniform volume, rectangular volume with just uniform parameters. What I'm going to do, I'm going to change first magnetic field. Magnetic field is what? Parameter number 13. Parameter number 13. I'm not going to change it much. I'm going to change it like by maybe, let's say, 30%. And again, thin line, just reference spectrum, will never change during our exercises. Now you see the new spectrum is below the reference one at the optically thick part, at the low frequency part. But at the high frequencies, the spectrum went up because the stronger magnetic field, the stronger the optically thin emission. This is expected. And this is basically not what we see here. See, we see that low frequency spectrum went down, but thin spectrum remains the same, at the same level. So let's go back to our sample program and try to modify to decrease the number of radiating electrons. The number of needed parameter is 12. So now 12 is 12, and we want to make it smaller than originally. Let's say something, or maybe same 30%. In this case, it's still too much, so let's try to do it 0.4. Now it's too small. Too large. 5. Okay, so they're fine. They get our sample spectrum, our sample spectrum, which behaves like we observed in our data. So what we are going to do next, we are going to do return to the model and try to play the same trick. Try to find a way to decrease the magnetic field in the model and decrease number of particles. We go here to the model, and we go here to the model, and first let's inspect our magnetic flux tube. Here you see the plot how the magnetic field depends on location along the central field line, and you see that it's not very typical magnetic field line. It reaches minimum at one of photospheric foot points here to the right, that corresponds to this point, and it reaches maximum here at the other one. So here the magnetic field is large, and at the end the magnetic field is low. So the idea is to move a little bit the entire cloud from the area of weak magnetic field towards area of strong magnetic field. And this can be done it's not just unique way of doing so, but there are a few ways. We can use this parameter, and this parameter enters equation for distribution of electrons along the red field line. And to see the effect of this change, I hit this button, update volume, and you just follow the green-blue volume at the left panel. So you see that the cloud as a whole moved to the right. And now let's see the effect of this move on our spectrum. Let's go back down profiles and click compute. And we expect something similar, but maybe more complicated, or not exactly quantitatively the same as we saw in our simplified model. So what happened here is that we moved the entire distribution towards area of stronger magnetic field, and as a result, we did not obtain a sufficient drop of optically thick emission, but instead we get significant increase of optically thin emission. But let's try to fix this issue first. This is reasonable. It is reasonable to expect from a practical point of view that when radio emission as a whole goes down, this corresponds to somehow decreasing number of non-thermal electrons. So let's go back to the model and let's decrease the number of radiating electrons to some extent. And let's recompute. So now it's much better. Now it's much better, and you see now you even have some lack of emission at the optically thick part. So we would want to get our emission here a little bit higher, and this means that we need a little bit weaker magnetic field. This means that that might mean that we moved our distribution a little bit too much here toward stronger magnetic field. Let's try to move it a little bit back. I will use this number and update volume. It moved back a little bit, but not to the original location. Original location corresponded to 0.3. We decrease magnetic field, and this implies that we likely have to increase a little bit the number of non-thermal electrons. I will use 5 in place of 4, just make test, and now compute it again. Not bad. So the agreement between model and data, which you see here, is example of acceptable agreement between data and model. So sometimes you will have better agreement, sometimes you will not be able to get really point-by-point agreement, but general trends like here, like here would be very will be acceptable.
Gregory, may I make a short comment?
Sure.
Maybe as a guidance, they may see here the standard deviation between the model and data. In this case, it's like 35%. Of course, ideally it would be 0, but in practice we don't get that low. But they should remember that when we started with the model in the paper, the time frame, we said around the same thing, 35%. So I would say from this perspective, we may say that this model is as good as the one we produce in the paper for the other time frame. So as a guidance, maybe when they will produce different time frame, if they succeed to get around this value or better, would be, I would say, consider a good result. Do you agree with that?
Yes, I meant to mention that, and I meant to say why it's relatively large, even so visual agreement here is very good. And the reason for that, one of the reasons, is these data points, which are not modeled and they're not part of our exercise. I think that we likely will produce another ref file where we get rid of this spectral area, just to facilitate more direct use of this measure. I think this will be helpful for the project implementations. But right now, I'm just oriented for visual impression in this spectral area. So I think that if we remove this area, we will have even much better metrics number. Yes, first I meant to ask if anyone has any question at this moment about what we have discussed before. If you do, please unmute your microphone and ask a question.
I have a question.
Sorry.
Oh, sorry. Go ahead. You first.
So my question is, because standard deviation accounts for the outliers on the side that we don't want to account for in our visual matching, do you think we are just trying to match the middle points of the graph without caring about the sides?
Yes, the goal is to match this spectral range. And to make it clear, we will prepare another file from which we just eliminate this spectral area, and you will be having like a clean case with the data only in the range you are actually fitting, you're actually developing your model.
Yeah, and also how easy is it to modify GX simulators so the standard deviation calculations only account for, say, the points in the range we want to match?
This is a very good question. I was thinking about it while Dr. Feshman suggested to remove points from the data. Another option would be to have some kind of slider in this area in which we can set a range in which we want to do the compute standard deviation for all. It would require more coding than removing the point, but it can be done. And I will be thinking about that for future. But on a short term, I think removing this point will do the same thing. And for long term, you are right. We might need to have some kind of option to put some markers for the range that we are interested in, and we want to model.
We are trying to adjust the parameters to make it fit the graph, but are there like orders of parameters in which we should adjust so it better fits the natural physical world? Because we can like manipulate variables in whichever way if we just want to fit the data points. But is there like a natural order that we like say one variable should be like going up while the others change naturally in a sense?
This is another very good question, and we've been thinking about that. In fact, a lot of knowledge is needed to do it not blindly, but objectively, and to facilitate this task. We created this program, which will be provided, which is already on the Dropbox. So what you will be assigned for the remaining time between this class and start of internship, play with this program and develop a document where you will investigate how change of each of the parameters listed here in this line, this means not all parameters, but only physical parameters, which means area, depth, temperature, minimum energy in electron distribution, maximum energy in electron distribution, spectral slope, number density of thermal plasma, number density of non-thermal electrons, magnetic field, and theta, which is angle between the magnetic field and line of sight, how each of these parameters affect the result. And to do so, you let me comment this out and come back to this one. And let me recompute. Yeah, so here I doubled the area and the spectrum moved up as a whole. Next one, I can double depth of the source. The depth becomes twice as initial. Run again. Nothing changed in optically thick part. Optically thin moved up by a factor of 2. Spectral peak moved up and to the right. Next one. I increase temperature of thermal plasma. Nothing changed. But if nothing changed at some point, it doesn't mean that nothing will change for any parameter combination. Let's make it a little bit smaller and compute emission for temperature 10 times lower than before. Nothing changed. Does it mean that will never change? 0.01. And now you see the change. You see additional absorption at the spectral peak area. Now, next parameter. Minimum energy of electrons. To understand what is it, you can refer to the JX simulator, to the model. You have a lot of different plots here inside JX simulator. You have thermal electron distribution in space. If you look here, you want to why we do not see anything? Jill, have you any idea why we do not see anything here?
It is there, but there is a surrounding plasma from the coronal part, which is overwhelming.
Uh-huh.
Okay,
Now you see the thermal distribution.
but
Hmm?
if you do that, you affect the result, yes, in the end, or not.
Yeah. But I affect, but the ambient plasma is irrelevant to what we have done.
Okay.
I would better remove it. Go back. No thermal distribution. The transverse to the flux in that direction, and this one distribution along that one, and this is the spectrum. So, and this panel shows you parameters how they define the area spectrum of non-thermal electrons. So this is number density at the peak of the distribution. There is two power laws with values 6.3 and 3.2. P mean is 18 keV, E break is here, 43 keV, and maximum energy is 2 MeV. So this is the meaning of these parameters. But let's come back to the program. So now we investigated somehow dependence on temperature. Next parameter is E mean. E mean it's 6. So you see that I've boosted the spectrum a lot, and it does not fit the plot any longer. Let's do that. Now you see the effect of E mean. Now let's consider what will happen with Emax. Nothing happens if I increase Emax further. This just tells us that electrons with energies above accepted Emax do not affect what they are doing. So let's try to decrease. So if you do not see any change when you change some parameter, it doesn't mean that this parameter never affects. There will be a range of parameters when and where variation of this parameter will affect your result. And you have to investigate and document all these variations, which will then guide your fine-tuning with the model. So let's try to make it 10 times smaller than before. You see that you have less and less high-frequency emission. But let's investigate at which point this change starts to be seen. If I decrease it just 2 times, almost no effect. You can see some deviation at the very end, 0.4. The deviation is visible, but small, 0.3. Bigger, 0.2. Even bigger, and again 0.1, very strong. And it goes further and further down with decrease of Emax. And this way you you can develop feeling of which parameters affect emission in which direction. General guidelines, not surprisingly, the larger the number of non-thermal electrons, the bigger in general will be emission. The bigger the magnetic field, the stronger the optically thin emission will be, and the weaker the optically thick emission will be. Increasing area, you will increase just proportionally the entire spectrum. Increasing depth, you will increase optically thin part and do not affect thick part. And slope, delta, the smaller the delta number, the flatter the spectrum and the higher the flux level. This is just main guidelines. And now let me come back to the tool and show shows the effect of these parameters in the model. Something like we just saw in the simplified case, how it changed in the model. And in particular, the simulator, for example, gives you many more ways of changing source area, for example. Source area, you may make more uniform distribution of electrons along the flux tube, and this will change area. And on top of that, this will change also the total number of electrons. So if we change this to, for example, 1, you see distribution became more uniform. To see it to the left, I update volume, and you see that it changed. And let's see now what is the effect of this change on the spectrum. Before we had just good match, but now we likely will see a spectrum boosted up. Reasonably strongly everywhere. So we have this change of the spectrum. Let's go back to the model and change this back to 8. What we can also do, we can go to geometry. And here you see cross-sectional radius of this loop. And we can just increase this reference radius. In this case, all our distributions, thermal and non-thermal, will be proportionally boosted in transverse direction. Let me do this. You see how this changed. I don't know, maybe recomputation of the grid is needed, maybe not, but it's safe to do so. And so it is similar effect, but the spectral peak did not move to the right as in previous case. So in previous case, we made the distribution of non-thermal electrons more uniform along the field line, and this meant that more electrons populated area with strong magnetic field. This means the contribution from strong magnetic field region became more essential, and this explains why spectral peak moved somewhere here. The bigger the magnetic field, the higher the spectral peak frequency in general case, in most cases. So now let's go back and maybe finally consider a couple examples how the change of fast non-thermal electron spectral parameters affect the spectrum. Here we go back to 4 grid points. And let's recompute to be safe. And go to electron energy distribution. First, let's make number density something like 3 times bigger. optically thin part went up and optically thick part went up. And I meant to note that even so we did not change the geometry itself, our object, our model flux tube, is not an object with sharp boundaries. The distribution of electrons continues outside the field lines we saw in the volume U, so it's a gradual decrease of electrons to the right and to the left in all directions. And this means that if we add more particles, we also effectively increase area from which the source seen as optically thick. Back here, 5 to the 7. And you see that here, maximum electron energies are assumed to be 2 MeV, and I want to investigate. Let me recompute it just for reference. Almost done. And I want to copy this picture. Maybe we want to compare it later on. Let's strongly increase it first. Let's make it 20 MeV in place of 2 MeV. Compute and see the result. So it doesn't seem that this change affects too much. But let's go back and consider smaller values, like 0.5, for example. So you can see the effect very clearly. You have insufficient number of high energy electrons, and the model high frequency emission decreased greatly. One can ask a question: what is the minimum value of this parameter sufficient to reproduce the spectrum? And we can try to address this question. We can put 1 MeV here and compute emission from the model. So you see now, still we have lack of emission. And this tells us that electrons above 1 MeV, between 1 and 2 MeV, are really needed to reproduce the spectrum. The final test with Emax, I will put 1.5, recomputed. So you see that 1.5 MeV is sufficient to give the match similar to what we had before. So this is the end of the second part of the class, and at this point again I want